Okay, in this video, we will learn more about the inference for the simple linear regression. And today we'll start with the inference for the mean response at some x. So what is this? Recall that our model is yi are all random variables. So the responses are random variables. It is equal to beta naught plus beta 1 times xi. This is a constant plus a noise term. This is also a random variable. And we assume that these random error terms are IID normal with mean 0 and variance sigma squared. So under this model, the true mean, so this is the thing we are interested in, the true mean response at some observed covariant value x, I, is this. So for a given covariant value xi, the mean of yi, this is the mean of yi, is beta naught plus beta 1 times xi. And we use this notation mu of y given xi to denote this mean at the covariance value xi. And when we want to estimate the mean response at a new covariant value x, so this is important. We need to do this within the range of these xi's, and we can estimate the true mean response at a new x using b naught plus b1 times xi. And this is the estimated mean response at x, and we use mu y given x hat to denote this estimated mean response. So that is just an estimation. The thing we are really interested in is the true mean response at that x. So we are interested in mu of y given x. So this is the true mean response, which is beta naught plus beta 1 times x. For the estimated version, we are using b1 and b naught. This is estimated version using the samples. So in order to get an idea of how good this estimate is, we need to do statistical inference using the confidence intervals and hypothesis testing to infer some knowledge about the true mean of y given a certain value of x. So if you just look at the distribution of a given x, it is just a normal distribution, and the mean is just the mu of y given x. Okay, so it is a normal at that x. Y is a normal with mean of y given x, and there is a variance sigma squared of y given x. So if you just look at the distribution at a specific x, it is just like what we did in the one sample inference. So under the model assumptions, this is what we have. The estimated mu of y given x is normally distributed with mean is mu of y given x. So the mean is the mean of the estimator is the true mean, which is beta naught plus beta 1 times x. That means, again, this is an unbiased estimator. And the variance of this estimator is this. So the variance of the estimator differs when the x changes. So for different x, you get different variances. Then we can construct a normal 0, 1 random variable by standardizing this random variable. So what we did is just subtract the mean and divide it with the standard deviation. So we subtract the mu of y given x, means the mean is just a mu of y given x, and the standard deviation is just the square root of the variance, which is this. So we have the standard deviation under here. So this standardized random variable, z, would have a normal 0, 1 distribution. But we don't know the true sigma in the model. So last time we talked about how to estimate the sigma parameter. And we used the SLF to estimate the unknown standard deviation sigma. So we replaced the sigma with SLF by plugging in the sigma into this form. And this big thing, we have a different distribution. It is no longer normal 0, 1. It will be a t distribution with n minus 2 degrees of freedom. And this would be our test statistic. So when you want to do this test, if your null hypothesis is that the mean response at a given covariance value x is a certain number, then you can use this test statistic. You just replace the mu of y given x, the true mean, with the number in the null hypothesis. Because in the null hypothesis, the test statistic is under the assumption that the null hypothesis is true. That's why you replace the true mean with the number in the null hypothesis. And this would have a Tn minus 2 degrees free distribution if H0 is true and the model is correct. So all the assumptions are met. And then a two-sided one-mass alpha confidence interval for the mean response at covariant value x would be this. So you have the estimate of mu of y given x here, and the quantile is t at minus 2, and it is 1 minus alpha over 2 quantile. And this part is again the standard error of mu of y given x hat. Okay, because it is sometimes you will also see this notation. It is a sample standard deviation of the estimator mu of y given x hat. Okay. So in the test statistic, you also find that in the denominator, it is always the standard error of estimator mu of y given x hat. Okay. So this is just a general view of what the form of test statistic and the form of confidence interval is like. And the one-sided intervals are analogous. So for the lower one-sided confidence interval, you just use the estimated mean, mu of y given x hat, minus, and for the one-sided confidence interval, you will use the quantile of t at -2, but it would be a 1 minus alpha quantile instead of 1 minus alpha over 2 quantile. And then times the standard error of mu of y given x hat. Again, the right end is positive infinity. So this is a lower 1 minus alpha confidence interval. Okay, so we will do the ceramic example again. So in this example, we have seen this a lot of times. The x, this is the predictor or the covariate variable. Is the pressure, and the response y is the density. So the first thing is that we will make a two-sided 95% confidence interval for a true mean density of the ceramic at 4,000 psi. So that is mu of y given x equals 4,000. Okay. And then we just plug in the estimated intercept and slope and x 4,000. So this is just a B0 and this is B1. And we got to 0.5697. In the quantile, t at -2 1 minus alpha over 2 is t13 because n is 15 here. We have 15 observations. And 1 minus alpha over 2 is 0.975 because it is 95% confidence interval. So looking up the table, you can check the table before, and you will get this number. So this is the quantile, and then you need this, the standard deviation of the mu y given x hat. So you plug in the n 15 here, and the x is 4,000, x bar is 6,000, and this sum of squares is 1.2 times 10 to the 8. SLF, so this is the estimate of sigma. SLF in this model with the data is 0.0199, and this is what we just obtained. It is 2.160. So the whole thing, there's a name for that. The whole thing is called the margin of error for this confidence interval. So the margin of error is 0.0136. Hence, the 95% confidence interval is just the estimator plus or minus the margin of error. Okay, so minus 0.0136 plus 0.0136. And the 95 two-sided confidence interval is therefore 2.5561 to 2.5833. And the interpretation is that we are 95% confident that the true mean density of the ceramic at 4,000 psi is between these two numbers. Okay, so this is about the mean density, mean response, the same as what we did in the one sample inference. So we are interested in the mean. And okay, so next we will calculate and interpret two-sided 95% confidence interval for the true mean density at 5,000 psi. So it is the same work. And then we will also test this hypothesis. H naught is beta naught is equal to 0, and the alternative is beta naught is not equal to 0, and the significance level alpha equals 0.05. And we will use the method of p-values. So for the 95% two-sided confidence interval for the true mean density of ceramic at the covariance value, which is the pressure equals 5,000 psi, is like this. So again, first you calculate this estimated mean response, mu of y given x hat. And then, so what you did is just plugging 5,000 to b naught plus b1 times x. Okay. And you get 2.6183. Then you calculate the margin of error. So for the 95% confidence interval, again, we will use the same quantile, T13.975. And the standard error will be different because you use a different x. So ACLF and x 5,000, x bar 6,000, and the sum of square in the denominator is again the same thing. So the margin of error you get would be 0.0118, and the 95% confidence interval is then again mu of y given x hat, the estimate of the mean, plus or minus the margin of error, and the 95% confidence interval is 2.6065 to 2.6301. Okay, and you can see that the width so the width of the confidence interval changes as your x value changes. This in 5,000 pressure, so when the covariant value is 5,000, the width is twice the margin of error. So the margin of error here is 0.0118. In the 4,000 case, the margin error is different. It is 0.0136. So for a different x, the width of the confidence interval will change. And the interpretation is that we are 95% confident that the true mean density, this is just mu of y given x, the parameter that we are interested in, the true mean density of the ceramic at 5,000 psi is between these two numbers. And for the hypothesis test, these are some formal steps. So the first step, you state the null and alternative hypothesis, and then the confidence level. The significance level. And beta naught is what? Mu of y given x is beta naught plus beta 1 times x. So mu of y given x equals 0 is beta naught plus beta 1 times 0. So it is beta naught. So beta naught is just mu of y given x equals 0. Okay. And the test statistic is in the numerator, it is mu of y given x hat minus mu of y given x. And in this case, mu of y given x hat is b naught plus b1 times x is 0 minus mu of y given x. So mu of y given x is mu of y given x equals 0. It is beta naught. So beta naught. So it is beta naught, b naught minus beta naught. And beta naught under H naught is 0. So it's beta naught minus 0. So in the numerator you have beta naught minus 0. And in the denominator, it is this formula, and the x is 0 here. So you plug in x equals 0 in the denominator here. Then this is the form of the test statistic. And assume H naught is true and the model assumption is correct, which is yi is a linear model. And the error terms are IID normal 0. So this is not 1, this is sigma squared. Then the test statistic would have a t distribution with n minus 2 degrees freedom. And in this example, because n is 15, so we have t 13. So this would be our reference distribution. So we plug in the data. We got the observed test statistic. B naught is 2.375. And you plug in x bar and the sum of squares in the denominator. Sample size 15 and SLF. And the observed y is 197.09. And because it is a two-sided test, so you want to get the p-value. So the p-value is a probability on the two tails. So it is a probability of that is a value, the absolute value of the test statistic is greater than the absolute value of the observed test statistic. So this T13 is just the test statistic T. We use the T13 here to indicate that the test statistic is a t-distribution with 13 degrees freedom. Okay, this is just the t, and this is just the absolute value of the observed test statistic. And this would be a very small p-value. It's a lot smaller than 0.001, and therefore is less than the significance level alpha of 0.05. Then we will reject H naught and conclude the alternative. So the conclusion in the layman's term would be that there is overwhelming evidence that the intercept of the true line is different from 0. Okay. The alternative is this, and not is it not equal to 0. So this is just a translation of that alternative hypothesis. Okay, so let's see the jump output. Actually, for that hypothesis testing, we can find everything we need in the jump output. So this is what we have in the jump output, and we will look at this table again, the preliminary estimates. And in the preliminary estimates table, we have seen the second row last time. So the second row, so here, this is just the estimated slope, which is beta 1, and this is the standard error of beta 1. The t ratio is b1 divided by standard error of b1, and this is used in this hypothesis. This is the test statistic we use in this hypothesis in order to test if the slope is 0 or not. And this is the p-value for this hypothesis testing. And then the first row. So for the first row, the estimate is just b1, b0, and the standard error is standard error of b0. Okay. And the t ratio is just b0 divided by standard error of b0. So this is exactly what we used here. Okay, this is just b0 divided by the standard error of b0. The denominator is just the standard error of b0. And we can find that we got the same number we have, which is 197.01, and this is the p-value. So this p-value is also for testing whether the intercept is 0 or not. Okay. So if you are doing this test, if you just want to test whether the intercept is 0 or not, you can just use this preliminary estimates table. The t ratio is the observed test statistic t, and this prob greater than absolute value of t is just the p-value for the test we just did. Estimate is b0, the estimated intercept, and the standard error is just the standard error, or the sample standard deviation of b0, which is just the denominator in the test statistic. And here is the issue of extrapolation again. So in this case and many other cases, this is one thing you need to be very careful about. B naught equals y of mu of y given x equals 0. So this x equals 0 is already beyond the range of our data. So we are actually doing some extrapolation. And estimating beyond the range of the covariant values is called extrapolation, and it will be dangerous for the linear regression. Okay, but in this case, we do this by assuming that the model is still true when x equals to 0. If the model is still true when x equals 0, then you can do the extrapolation. And in some special cases, you can always do the extrapolation. So, for example, when you know the process or the system very well, and you can describe it with the right equations, and these equations might not be a linear equation, and you will estimate the parameters of the model using the nonlinear regression. So, for example, when you know the true relationship between y and x is like this. So it is theta 1 times x divided by theta 2 times plus x. So, and there is an error, random error. And if you know the true system is like this, then you can estimate the parameters theta 1 and theta 2 using nonlinear regression. And then you can do the extrapolation because you know the relationship between y and x is always like this, no matter what the x is. Although you only have the data within a certain range of x, but you know that this is the true. You know this is always true for all x. Okay, then you can do the extrapolation once you have estimated the parameters using nonlinear regression. And for nonlinear regressions, you can check this book, Nonlinear Regression Analysis and Its Applications by Bates and Woods. Okay, that is a confidence interval and hypothesis testing for the mean response y at some x. And then next we will see the prediction intervals for a new y at some x. So remember in the one sample case, in the one sample inference, so a prediction interval is for a new or the next data point xn plus 1. Okay, so it is a random variable. And the PI is wider than confidence interval due to more uncertainty. Okay, so it's a thing here. We want to use a prediction interval. So for the one sample case, if you want to get a prediction interval, is to capture the next data point xm plus 1 with some confidence. And the prediction interval in simple linear regression is also to try to capture the next response the given value of a predictor variable. So that is the new y at some x. And the response y, the next response y is a random variable. So that's why it's called a prediction interval. And a two-sided prediction interval for a new response y at some x is this. So it's everything is the same as confidence interval. The only difference is that we have a 1 plus here. And then you will see that, like in the one sample inference case, the prediction interval is also wider than CI, right? Because we have an extra 1 in the margin of error. This is also due to more uncertainty. Why? So because for example, so y is equal to mu of y given x plus an error. So you don't know the true mean, and there is also an extra uncertainty in this random error terms. So you will need a wider interval to capture the y than the interval to capture just the mean response because of this extra error term. Okay, so this y is actually introduced by this error term epsilon. And the one-sided intervals will be analogous. Okay, for the one-sided, so this part would just be Tm minus 2, 1 minus alpha. Okay, yeah, the other things are the same. Okay, now this example is again the ceramic example. We will make a two-sided 95% protection interval for the next density of the ceramic at 5,000 psi. And the first thing is, again, we will get the mu hat y given x. So this is the estimated mean response at x equals 4,000. And the quantile is still the same, but the margin of error will be different because there is a 1 plus in the standard error term. And when you plug in everything to the formula, the margin of error would be 0.0451. And then mu y given x hat plus or minus the margin of error gives you this prediction interval. So if you check the previous confidence interval for mu of y given x at 4,000 psi, you will see that this will be wider than CI for the 4,000 psi. The interpretation would be we are 95% confident that the next collected density of the ceramics at this predictor value and the predictor is the pressure. So the next collected density of the ceramic at 4,000 psi will be between these two numbers. Okay, the one last thing for today is the simultaneous confidence interval for mu of y given x. So what is the simultaneous confidence intervals and where the problem comes? So sometimes, so the simultaneous confidence intervals comes with these situations. Sometimes you want to do inference on a bunch of means. So for example, you want to do this mu of y given x equal 2000, x equals 4000, x equals 6000, etc. at once. And when you compute several confidence intervals at once or do multiple tests at once, so when you do inference for a lot of parameters at once, you will need to account for the simultaneity. So what is this simultaneity? Here is an example. So on average, if you do 20 tests at the same time and you do it independently, and each test has a significance level alpha equals to 0.05, we will expect that one of those tests to reject H0 and conclude HA by chance. Why? Because the alpha is just the type 1 error. The type 1 error is when is that you reject H0, assuming H0 is true. Okay. So if the H0 is actually true and you do 20 tests, and in these 20 tests, because of the type 1 error is 0.05, then you're very likely to get one test that is rejected, that rejecting the null hypothesis. Okay, that is the issue of doing multiple tests simultaneously. So then the simultaneous type 1 error will be very high in this case, because if we just set the significance level alpha equals 0.05 for each of these 20 tests, then in the type 1 error, you can imagine it's very close to 1, because you always get for most of the time you always get at least one test to reject H0 among these 20 tests. Okay, because your type 1 error is 0.05. And I think this cartoon explained the problem very well. So there are two persons, A and B. A said that jelly beans cause acne, and B said, scientists investigate. Okay, and then scientists do the investigation, and they said, we found no link between jelly beans and acne. The p-value is greater than 0.05. And they said, that settles it. And B does not agree. She said, I hear that it's only a certain color that caused it. Then they said, scientists do the test for a lot of colors of jelly beans. We found no link between purple jelly beans and acne. The p-value is greater than 0.05. No link between brown jelly beans and acne. no link between pink jelly beans and acne. So they got a lot of p-values that is greater than 0.05, which shows no significant result, no link between jelly beans and acne, no link between gray jelly beans and acne, no link between tan jelly bean and acne. And in one test, they finally get a significance result. We found a link between green jelly beans and acne, p is less than 0.05. And they say, wow. And they continue to the test for a lot of jelly beans. And totally they did, if I check, there are 20 tests. They did 20 tests independently. Okay. And among these 20 tests, they get one test gives them a p-value of 0.05. But if you have an idea of the type 1 error, then you know that if type 1 error is a 0.05, you should expect that you get a rejection in these 20 tests if the type 1 error is 0.05, because that is the error you made. That one test is the error you made. But they don't know. Then in the next day's news, there is an article that green jelly beans linked to acne and 95% confidence. So this is a problem caused by multiple tests. So in this case, you need to consider the simultaneity. So what you do is that if you have k-simultaneous tests and you want and each with type 1 error alpha, so the significance level is alpha, then the type 1 error for the simultaneous tests. So the type 1 error for all tests together at the same time is that the probability you get at least one rejection in the k-tests. Okay. Since for each of the tests the probability of rejection is alpha, and the probability of at least one rejection in these k-tests is obviously greater than alpha because you have a lot of tests. And there is an extreme case. If these tests are independent and the actual type 1 error would be, there is the probability of at least one rejection in these k-tests is 1 minus the probability of the opposite case. The opposite case is that the opposite of at least one rejection is that no rejection in these k-tests. Because these tests are independent, then use 1 minus the product of the probability of you fail to reject each of the case. The probability of fail to reject the ith test, and it is 1 minus alpha to the power k. Okay. And this would be very close to 1, right? Even if you got 0.95, you got alpha equals 0.05, 1 minus alpha is 0.95. So the probability for each of them to fail to reject the ith test is high. But if you multiply it 20 times, then this would be very close to 0. And the type 1 error would be extremely high. It would be closing to 1. Okay, so this is the issue of simultaneous tests. explained in a mathematical way. And the simultaneous confidence interval is the same thing. So if you have k confidence intervals for mu1 and mu k, and we denote the corresponding random intervals for the confidence intervals of this as I1 to ik. Then if the confidence level for each of this is 1 minus alpha, then you have this. So this is by the definition of 1 minus alpha confidence interval. Mu I is within this random interval. The probability that mu I is within this random interval is 1 minus alpha for each k. And then the simultaneous confidence level would be the probability that each mu I is contained in the random interval I. Mu1 is in I1, mu2 is in I2, and mu k is in Ik at the same time. So this probability by intuition would also would obviously be less than 1 minus alpha, right? Because for each of these events, the probability of happening is 1 minus alpha. And then the probability of these events happening at the same time should be less than 1 minus alpha. And in the extreme case, when these events are independent, then this probability will be 1 minus alpha to the power k, which will be close to 0. Okay, if k is big and alpha is like 0.05. So the confidence level would be a very small number. This is not something you want. And this also explained if you want to get a 1 minus alpha simultaneous confidence level, the simultaneous confidence interval should be wider than the individual confidence interval, right? Because if you just use 1 minus alpha for each confidence interval, then the simultaneous confidence level is something less than 1 minus alpha. And if you want to achieve the 1 minus alpha confidence interval, simultaneous confidence level, then for each of the confidence interval, the individual confidence level should be greater than 1 minus alpha. Okay, so we have explained what the simultaneous confidence intervals is. And in SLR model, what is the simultaneous confidence intervals? So let Ix be the random intervals for the simultaneous 1 minus alpha confidence intervals for mu of y given x. And what we want is this. We want mu of y given x covered by Ix and at the same time for all x. This probability should be 1 minus alpha. So it is the mean of response at x contained in Ix at the same time for all x. So infinite. There's infinite events happening at the same time. Okay, because x has infinite possible values. And how do you get such simultaneous confidence intervals? It turns out this probability This kind of confidence interval can be obtained using this formula. So that here you again have a mu of y given x hat, the estimated mean at x, and you also have a standard error of mu of y given x hat, but the quantile here is different. Before it is so for the non-simultaneous case, it is t of n minus 1 and 1 minus alpha over 2 for the two-sided confidence interval. And here you have this. It is an a quantile of the F distribution with 2 and n minus 2 degrees of freedom. And there is also a constant 2 here and a square root. And this formula will account for the fact that we are computing k confidence intervals at the same time. K can be arbitrary number. Okay, it can be any number because we have considered all possible x, infinite x at the same time. So if you're computing k simultaneous confidence intervals, then no matter how large the k will be, the formula will always be this one. Okay. So this shows the confidence region. The confidence region is obtained by making the simultaneous confidence intervals for all x and connecting them. So you calculate the simultaneous confidence intervals for this x. So for each of the x, it is a simultaneous confidence interval. And you connect the upper and the lower bound. So connecting the upper bonds, and you can connecting the lower bonds, and you get these two curves. And you get these two curves. And the region between these two curves would be called a simultaneous confidence region for all mean responses. So what does this mean? That means you are 95% confident so if it is a 95% simultaneous confidence intervals, then and then you get this confidence region, and we can say that we're 95% confident the true line will fall in this region. We are 95% confident that the true line, maybe the true line is here. We are 95% confident that the true line, the whole line, will be covered by this confidence region. Okay, but you don't know whether this true line will be covered in the confidence region or not. You're only 95% confident that this is true. And therefore, this can be used to test if the true line is, for example, y equals 0. Okay. And in this case, let's say this is 0 here, then y equals 0 is this line. So you can see that y equals 0 is not covered by this region. So reject. The line is not y equals 0. Okay. And if you want to test if the line is y equals to x, so for example, this is the line y equals x, and it is completely covered by the region, and then you will fail to reject this hypothesis. Okay, and you will conclude that it is plausible that the true line is y equals x. This is what you can do with this simultaneous confidence intervals and the confidence region you obtain from the simultaneous confidence intervals. So it is about a bunch of intervals containing the whole true line, because you're constructing infinite confidence intervals for infinite number of x at the same time. So that literally means that you're constructing a confidence intervals for the whole line. Okay, the whole true line. Okay, this is an example of the ceramics data. So you would just use this formula, and we have already have all of this. The only thing we need now is this number. And we first find this number because we want to get a 95% confidence simultaneous confidence intervals. So we have 1 minus alpha here. So this is one thing you need to be very careful about. So simultaneous CI is two-sided, but the quantile we use in the F distribution is 1 minus alpha quantile. So it's not like the two-sided confidence interval we did for each mu of y given x. If it is two-sided, we use 1 minus L over 2 quantile for the t distribution. Here it is a two-sided, but we still use 1 minus alpha quantile. And this number is 3.81. And then we plug in B0 and B1. This is the x. It can be any x. And this is the margin of error. And we also have an x changing. So this is what we have for the simultaneous confidence intervals for any x. And if we only want to have this 5 simultaneous confidence intervals for these 5x, we just need to plug in the x to this form, and then we get this confidence intervals, simultaneous confidence intervals. So you can also plot the simultaneous confidence intervals in JUMP. This is using fit y by x method. Once you get the fitting line, you can click on the linear fit and you click on the confit curve fit. This will give you more confidence regions. And this is actually the prediction interval. This confit curves indiv is not the individual confidence intervals, but it is the prediction intervals. Yeah, and then you got to dashed lines indicating the limits of the simultaneous confidence intervals, and you can also do the confit shaded fit, and then this area will be filled with light red color, so the shaded region between these two dashed lines is just the confidence region. And by default, so this would be the 95% confidence region by default. And to calculate the lower limit and upper limit for the simultaneous confidence intervals for each x, you can do this. You first create a new column called simultaneous confidence margin of error. So we use the column to calculate the margin of error. And you need to click on the formula here. And in this formula, you put on this formula. And this gives you the margin of error. And then you can create 2 more columns, which is the lower bound and upper bound. So for the lower bound, this is just a mu. This is just a mu of y given x hat, the estimated mean at x, which is pressure, and minus the simultaneous confidence margin of error. The upper bound will just plus the simultaneous confidence intervals marginal error. And then these two columns gives you the lower bound and the upper bound for the simultaneous confidence intervals. Okay, there will be a video showing you how to do this in JUMP. If you're not very clear about the process, to go to check that video. That is all for the simple linear regression.